Okay, in this video I just want to cover another titration curve problem because, more practice, and I'm not sure I explained it in the first video as well as I would have liked, so let's try another one. This problem says, draw the appropriate titration curve for the tripeptide meth lyse loose, starting at pH 1 and ending at pH 12. On the curve, label the pKa's and the pi, show the buffering regions and the equivalence points. Okay, well, essentially what we have here is we have this tripeptide, methionine, lysine, and leucine in solution, and we're going to be adding NaOH to that solution to essentially make it more basic, and as it becomes more basic, protons are going to fall off at different values. So the first thing to do is, at pH 1, we already know that this is a really low pH, it's a very acidic condition, so everything's going to be protonated. So let's just draw a picture of the tripeptide completely protonated. So NH3, it's got a positive charge here, and this is CH2, CH2S, CH3. So peptide bond, NH, we've got lysine here, so CH2, 4, NH3 plus, and the last one is leucine, so that's CH, and that's CH2, CH, CH3, CH3. And that has this group on the end here, this carboxyl group on the end here, and it's got its proton. Okay, so that's the tripeptide, and that's the first step. We want to draw it fully protonated. Now we want to see what the overall charge of the peptide is. So there's a +1 here, there's a +1 here, and those are the only two charges on it, so the overall charge is +2. So now that we know what the overall charge is, we essentially want to locate, probably on a chart, like I said, that will most likely be given to you, where these are going to lose, at what pKa value would this amine group lose its proton, at which value will this lysine lose its proton, and at what value will this carboxyl group lose its proton. So this one over here will be at a pH of about 3.5. The amine group over here will be at a pH of about 8.5, and the lysine down here will be at a pH of about 10.5. So now that I know where these three are going to lose their proton, at what pH they're going to lose their proton, I say we start with a +2 overall charge, and then we look for the pK1. And the pK1 corresponds to the first group to lose its proton, so that's the carboxy group over here. So this is pK1, and that's 3.5, and that brings us to a +1 overall charge on the molecule. So once we have that, we'll go to pK2, and we'll look for the second group at which we're going to lose a proton, and that is going to be over here, the 8.5 on the amine group. So now that we know that, we can write up here that this is pK2, and that gives us a 0 overall charge. And the last group to lose its proton is going to be the lysine, because that's at 10.5. So that becomes pK3, so pK3, and that gives us a -1 overall charge for this molecule. So now that we have all that taken care of, we can draw the titration curve. So that's the next thing I'm going to do here. So I'm going to make a little x and y axis. This is going to be equivalence of NaOH, so how much NaOH I'm adding. This is going to be the corresponding pH, and I'll label 3.5, 8.5, 10.5, And I'm just going to use those values arbitrarily. I mean, you can make this a little more close, or if you could put values in between if you choose to. So what I'll do is I'll draw this up and I'll flatten the curve out around 3.5, and I'll put my point in there at 3.5, you know, signaling that that's one of the equivalence points. One of the things I want to do is maybe just use like an orange marker here to kind of mark that spot as 3.5. And then we'll travel up to 8.5, flatten the curve out here, make another mark there, indicating that we have another equivalence point, another point at 8.5, and then we'll travel up to 10.5, level off there, make another mark at 10.5, and then this just goes like that, essentially. So that's pretty much what we wind up with. This over here corresponds to PK1, this corresponds to PK2, and this one corresponds to PK3. So that's all labeled. They also want us to label the buffering regions and the equivalence points. So I'm just going to use a squiggly line here and call that my buffering region. And again, recall that the buffering region is strongest when the pH is equal to the pKa, but it also extends for plus or minus 1 pKa unit for each group. So now that we have that, we can also show the other part here and the other point here. Those are also good buffering regions here and here. So those are your three buffering regions, and we also can label the equivalence points, which this will be 1 equivalence, 2 equivalence, and 3 equivalence. So that's pretty much all you need to label on the graph. The last thing to do here is to calculate the PI, and remember that's the isoelectric point. So I'll move down here and I'll say the PI is equal to, and if you recall, the PI is equal to the point at which we cross from +1 to -1 through the 0. And what you want to do is you want to use the pK2 and the pK3 value, add those two together and divide by 2. So essentially you're taking the point right in the middle, which is where the molecule has a charge of 0, or an overall charge of 0. So what I want to do is I want to say 1/2, and now if we recall here, we labeled them, so pK2 over here corresponds to 8.5, and PK2 and PK3 corresponds to 10.5. So we'll put those two in, 8.5 plus 10.5. And divide by 2. And what we'll find is that the PI is equal to 9.5. So that's the point at which the tripeptide carries no formal charge. And that's about it. That's all you have to do to draw the titration curve. So they're fairly lengthy problems, and I can almost assure you that you'll see something like this on an exam or a quiz. It's a very common problem. I did several of them, so thanks.